essentials.
Okay. All right, so here's the drill for today. So we'll go over this last assignment, make sure everybody's cool with that. Make sure nobody has any questions on that. Then we're going to work through like this big complex problem that's going to be on the test tomorrow. And then I'll give out the review and there we go. So now tomorrow, if at all possible, if you can come back during fourth block and take the test, that would be cool, because that way everybody can test at once. You don't have to, okay? If you can't, okay, whatever, just let me know and then I'll email you the test. So is everybody going to plan on coming back to the test tomorrow?
Sure. Yeah.
Okay. Now, you're going to have to check in through the office, make sure you're wearing your mask, and have to take your temperature with the whole smash, okay? So I would suggest maybe you get here, I'd say around 1 o'clock, so that way you have time to get down here in plenty of time. So I'm probably going to have you guys either sitting in the back of the room here or going next door, so that way I can keep everybody spread out, okay? So now my normal Tuesday group, they're going to be here, so they're already going to kind of have dibs on their table, so don't come in and go, that's my table. Well, no, that's your table on Mondays and Thursdays. It's their table on Tuesdays and Fridays, so don't come in here and go, hey, you're sitting in my spot. No, no. If they come in, you can do the same thing if we have the test on your day. So, so that's what's going to happen tomorrow. We don't have a lot of tests, but they tend to take a while because I kind of write them like the AP test. So I'm just telling you, now this first test is not timed. Okay, now I'm not going to give you until 6 o'clock tomorrow night, to get down with the test. I mean, that's completely reasonable. Because my take is that, okay, if you know the material, you can get through the test in plenty of time. If you don't know, that's like, oh, you're struggling. It's like, that's what I'm going to draw the line. So I'm not going to say, oh, you have until exactly 3 o'clock. But it's also, if it takes longer than that. So if you're a slow test taker, you might kind of allow for that opportunity. Okay, so let's talk about that last set of problems. So on 4A, if 4A is wrong, everything else is going to be wrong. So that answer to 4A should be around 21 meters per second. Okay? If that's wrong, everything else is going to be wrong. So you should have a position time graph that's going to look like this. And you should have a velocity time graph that's going to look like this. It's going to start at about 21, go to negative 21, slope of negative 9.8 meters per second. Huh?
We're supposed to write this one.
No.
Okay.
I'm just saying that's what I'm just telling you that's what the slope is going to be.
Okay.
Okay?
Thanks.
Yep. Now, when you get down to 4D, okay, here's the magic code, right? When I ask you what's the slope of the position time graph, I don't want you to actually draw the lines. The magic code is that when I say, hey, what's the slope of the position time graph at an instant in time, what am I asking you to actually find? The instantaneous velocity at that point, okay? Now, don't tell me your initial velocity is 0. No, okay? Don't tell me when it lands, it's 0, okay? That's not it either. It's not going to go very high if your initial velocity is 0, okay? It's like, initial velocity is 0, go. Okay, well that didn't go so well. It has to be like some positive number. So the idea being is that your tangent lines have become more and more shallow. Eventually your tangent lines are going to become 0. Then they're going to become negative and become steep. Also, you have to understand the terminology. When I'm asking about speed, okay, so on this problem, you're going to have the same speed twice. Once when it's launched and once when it lands. Because speed is just the magnitude, okay, that's it. It's just the scalar quantity. So it's going to have the same speed when it's launched the same speed when it lands, assuming that it returns back to that same point. So the speed's going to be the same. Velocity is going to be different. Okay, so the velocities are going to have the same magnitude, but they're going to be in opposite directions. So on the test, make sure that you understand the difference between speed being a scalar quantity and velocity being a vector quantity. So velocity is just speed with a direction. Okay, that's the short version. Okay, on number 5, make sure, and 6, make sure you do not have the words backwards, okay? This has nothing whatsoever to do with going backwards, okay? So don't, oh, if it has negative velocity, it's in reverse. No, it has nothing to do with it. Negative velocity is just however you define your system, okay? And it isn't falling back to Earth. Negative just means it's going in a particular direction, okay? So on 5 and 6, make sure that you don't have anything involving the words backwards, okay? Now, on number 8, your velocity time graph should look something like this. Okay? So, you got the 2 spaceships. One's going at 600 meters per second, the other one's going at 450. So imagine here are the 2 spaceships. They're at this point in time. One's going 600, one's going 450. They're going to go out, they're going to stop, and then they'll come back at that same point in time. Okay? So tick, tick. So make sure that you label the slopes of these lines. Okay? Or at least I know which one is which. Which one is Columbia and which one is Enterprise. And if all goes well, one acceleration should be around -10, and the other acceleration should be around -15. Okay? That's an ish, but that's about where your 2 accelerations should be on number 8. One around -10, the other one around -15. Cool with that? Okay. Now, I promise you on number 9, there is going to be a problem like number 9 on the test. I promise you. Okay? I promise you. So, here's your rocket. Okay? And that initial velocity is going to be 0. Yes? Thank you. Okay. So, here's the deal. So you're going to take off and you're going to go from 0 to 30 meters per second at a height of 25 meters, as I recall. Okay. So the first thing you want to find is the acceleration. Now, here's what you cannot do. Okay? Here's what you cannot do. You don't get hung up and go, oh, I can find the time. I'm going to take 25 meters and divide that by 30.0 meters per second to get my time. Okay? Why can you not do that to get time?
Because you're accelerating from...
Exactly. You're accelerating. You're trying to use displacement equals velocity times time, which is a wonderful equation. Don't get me wrong. Okay? It's cool. Doesn't work because of the fact that you are accelerating. So don't take 25 meters and divide it by 30 meters per second to get the time. Train wreck. Won't work. What you can do is you can find your acceleration using that equation. Okay? You can find your acceleration doing that. Then you can find your time from there. So your time on number 9 should be a little bit less than 2 seconds. Okay? A little bit less than 2 seconds. And your acceleration should be something close to your current age, if not your exact current age. I'd like to say I had that planned out. I didn't. It was just random. Okay? I don't put that much thought into my problems. Okay, now here's the bigger kicker. On number 9, so here's this rocket engine. We fired it, went up, 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 up. Okay? It's going faster and faster and faster. At that point, we shut off the rocket engines. At that point, what's the only force left acting on the rocket?
Gravity.
Gravity. Okay? What's the acceleration due to gravity? Yeah, do not make that second point, when you, at that point we shut off the engines, what's the velocity, what's the acceleration? There's nothing to calculate, okay? It's just like me throwing this up in the air. As soon as I let go of it, I know that acceleration is going to be negative 9.80 meters per second squared. There's nothing to calculate. That's the number. Boom. That's it. Okay? So on your time, so here's what happens. On your velocity time graph, you started at 0, you went up to 30 meters per second, and then you're going to slow down back to 0. Okay? Now, down there on number 10, pay attention to everything that I want on that velocity time graph. Okay? I want you to label the slopes of the line, and here's what's most important, and I'm going to tell you this on the test tomorrow. You have to keep like a running clock. So you had about 2 seconds to get to when you fired the rocket engines, okay? Then it took about another 3 seconds for it to stop. But you want to add those 3 seconds to that initial time. Don't come out here and make that mark at about 3 seconds. That isn't what happened. That was an additional 3 seconds beyond the initial firing of the rocket engines, okay? So this is why you have to keep a running clock, all right? So you're starting here, you're there, boom, you're going out like that. We good?
But yeah, I just moved it forward so I could write, and it moved that slightly.
Oh, okay.
But I don't know. I'm gonna fix it a little bit. You carry on.
Okay, all right, thanks. Okay. So make sure on number 10 that you have labeled everything that I want on that graph. Okay? All right. Let's talk about the mini lab. So there's a couple of ways that you can calculate that initial velocity. The easiest thing to do is just make a sketch of this velocity time graph where it goes something like this. Like, what was your guys' times? Like 1.2 seconds, something like that? Okay, so let's just say it was 1.2. So that's at about 0.6 seconds when it's at its maximum height. You know how high it went, so you know the area of that triangle. So you can go, oh, area of a triangle is 1/2 base times height. You know the area because you know how high it went. You know the base because you know half the time. Find your height. There you go. Now, everybody's numbers is different. In big, bold letters, I tell you, show every step of every calculation, okay? I am not going to guess. Some of you really need to work on your organizational skills, okay? Because what you do is you randomly write down numbers with no units, no formulas, and nothing, and then you expect me to sort it out. That train is not going to leave the station anymore. If you want me to begin to hope to follow what you have done, you had better do. It's okay.
I just had some.
I know. A good job of keeping this thing organized. Because I swear to you, as soon as I can't follow what you have done on this mini lab, that's the point that I quit grading. I don't care what the numbers are. You show me, oh, here's what's on the way up. Here's my acceleration. Here's what's happening on the way down. Here's that acceleration. Keep it simple for me to grade. View this from my perspective, not your perspective. Okay? Imagine you're on the other side of the iPad trying to do this. Now, I'm not doing that to be a joke. I'm doing that because that's how science is done. Somebody should be able to take your lab reports and exactly follow what you've done. Random numbers with no units and no formulas isn't a lab report. Okay? You're just writing down random numbers and hoping something sticks and that you get an answer. It's not how science is done. Science is a means of communication, especially on lab reports. So, I should be able to take Ryan's and give his to Lauren, and Lauren should be able to act like she has no clue what's happening in the lab and exactly follow every calculation that he has done. Okay? So, if you're not sure, give it to someone else and go, hey, you know, look at my stuff. Can you follow what I've done? And if they go, man, I did the lab and I have no idea what you were doing, that's probably a train wreck, okay? So I'm just saying. When you calculate that experimental error, remember that's an absolute value of theoretical minus experimental divided by theoretical times 100. So in this case, you're going to take negative 9.8 meters per second squared minus whatever you get divided by negative 9.8 meters per second squared times 100. So keep in mind this is going to be negative minus a negative divided by a negative multiplied by 100. Okay? And I think I ran the numbers. I think with the data you guys got, I think you got an acceleration of like around negative 10.
Yeah.
Something like that. So it was actually pretty close. So anyway, pretty small experimental error. On the graphs, you should have a total of 6. Okay, make sure that they are clearly numbered so I know which ones they are. Now, if you want to hold on to this, well, you guys already have it. But if you guys want to go ahead and scan it, send it in, that's cool. Okay, that way I can get it graded. If you get this sent in to me relatively quickly, I'll get it graded and sent back to you. So you can know if you're doing it right, doing it wrong. Okay? So, any questions on that one? I beg of you, keep your graphs organized. If nothing else, label them. Okay? So that, again, don't expect me to know what a random graph is. Okay? I'm not going to know. And I'm not going to waste my time trying to figure it out. Okay? You all are big people now. So do that. And make sure that you take a picture of both sides of like the labs. Because I've got some people that are just taking like a picture of the front and not the back. And it's like, really? So make sure that, and look at your graph, look at your pictures before you send them. If they're like grainy and not in focus, guess what? They're going to be grainy and not in focus when they get to me. It isn't like they're magically going to get better when you send it to me as a PDF file. Okay? Seriously. Don't be afraid to like retake the pictures. Okay. So here's what we're going to do. So you in the studio audience should already have this little slip of paper. So what this is this big complex problem. It's going to tie together, and I'm going to give you all this piece of paper in just a second. I just want to set the stage. So here's this building, and it is 8 meters tall. All right. So to give you some perspective, this ceiling is about 2.5 meters tall. Okay. So it's up there a ways. Okay. So you're going to throw a ball straight up with an initial velocity of 12.0 meters per second. And it's going to go up, and then we're going to let it fall all the way down to the ground. Okay? So you got 8 meters, you got 12 meters per second. So what I want is that you're going to go through and you're going to calculate like the maximum height, time up, time down, time total, the velocity at impact, the position time, and the velocity time graphs. So here's why this is important. Number one, it kind of synthesizes about everything that we have done. I promise you, okay, on the test tomorrow, this is going to be the last problem on the test. It's going to be worth more points than any other problem on the test. I promise you, this is going to be it. The only thing I'm going to do is I'm going to change the numbers. Okay? So here's what I want you all to do. I want you to act like this is the test, and I want you to work this problem. Okay? This is going to give you an indication of how well you're doing. So when you get an aspect of this problem done, okay, you don't have to have the whole thing done. But I'm going to rewrite these parts up here. And so what I want you to do is that when you get a part of it done, max height, time up, time down, whatever it is, here's what I want. I want 3 things. I want the solved equation, Okay? Like you're gonna have time equals however you're gonna calculate time. Then I want the numbers substituted in with the correct units and the correct signs. And then I want the final answer with the correct number of significant digits, and I've given you like 3 significant digits in all of these measurements. That's what's going to happen on the test. Okay? So I want the solved equation. I don't want what you start with. I want the solved equation. Now, if you don't have to solve it and it's a straight up equation, hey, that's great. There's nothing to solve. But if you have to solve it, I want it solved. Okay? I don't want to see the steps to solve it. I just want the final solved equation. I want the numbers with the units, and then I want the answer. Because this is what I'm going to look for on the test tomorrow. Okay? Part of your grade on this problem is the thoroughness of your work and my ability to follow what you have done. So to make sure everybody's starting the same way, we're defining the ground as being the reference point, that's 0. Everything going up positive is positive, whether that's velocity, acceleration, displacement. Anything going down is going to be negative, velocity, acceleration, displacement going down. Okay? So, get out a piece of paper, whatever you want to work on. I want you to work the problem, pretend that this is the test, and then when you get an aspect of it done, come up here and write it on the board. So, Evan, stop that for a second. Okay, so,
Oh.
what?
Wait, never mind, actually.
Okay. All right, so let's talk about let's start with the time up, okay? So let me go down to, who did this one?
The one at the very bottom.
Yeah, right. Brady did this one. So here's the deal. So let's talk about this. If it were me, this is how I would work this problem, okay? Now, the Bodie method, okay, we'll go up here. Here's why I wouldn't do this. Because you went off of that maximum height of 7.35. And it was a god-awful a lot of algebra to do. Now, it worked, okay? But here's the problem. If your maximum height is wrong, then your time up is going to be wrong. So, in a problem like this, you want to try and work with given values as long as you possibly can, okay? So, this works, I wouldn't recommend it, okay? Because, number one, it's complicated, and you're using that 7.35, which is wrong, so like if you're Lauren, if you happen to have the wrong height, then everything else is going to be a train wreck as well. It works, I just wouldn't recommend it, okay? Now, so let's go down and talk about this time up. So before you do any calculations, when you see that initial velocity of 12 meters per second, right away, why do you know that your time up has to be more than 1 second?
Because your acceleration downward is smaller than your initial velocity.
Yeah. Okay, your acceleration is negative 9.8 meters per second squared. So when you draw that velocity time graph, okay, and you're starting up here at 12.0 meters per second, and this thing is going to come down like this, the slope of that line is negative 9.8 meters per second squared. So right away, I know if I start at 12 meters per second, 1 second later, I'm going to subtract 9.8, which isn't going to get me to 0. It's like you show up at the mall and you have $12. Mom and Dad say you've got to spend $9.80 for every second that you're there. Okay? Now, later on, once we get into gravity, this is going to be the fee that's charged by the gravity mafia. Okay, we'll get to the gravity mafia really when we talk about forces. But basically, the gravity mafia is going to charge you $9.80 to operate on the Earth. Okay, so you start with $12. The gravity mafia goes, huh? You're a good boy, huh? You're going to take $9.80 from me. Okay, so at the end of 1 second, okay, they have stolen $9.80 from you. You still have some money left over, but not much. So this is also why I know my time up has to be more than a second, but it's going to be less than 2 seconds because I'm not at $19.60. So before you even start the problem, look at this and go, okay, what's my time up going to be? Okay, it's more than 9.8, less than 19.6. It's going to be 1 and some change. Okay, so get an idea of what that answer is going to be before you even start. Okay, so you do this, and this is what's nice, and this is what I'm going to look for on the test. Okay, so this is the level of work that I'm going to expect to see. And y'all did a wonderful job. So here's the equation, v minus v naught over my acceleration. I got 0 minus 12 meters per second. Notice that this is negative value. That's what I'm going to look for. Okay, I'm going to look for some of the points on this big problem are going to be you consistently using the correct sign of the acceleration. So this is something I'm going to look for on the test. Did you use negative 9.8 meters per second squared consistently? Okay? So we get this, we got 1.22 seconds. So at this point out in time, we're at 1.22 seconds. Okay, so we got that number, right? So we're cool. Now, let's talk about the maximum height. There's 3 different ways that you can find the maximum height. Joelle, did you do this one?
The top one?
Yes. Okay. So Joelle did the top one. Now this is where this is nice. Okay? So I've got the solved equation, v squared minus v naught squared over 2a. And the maximum height, right, your final velocity is going to be 0. You know your initial velocity, you know g. I added the 8 meters. Now, technically, okay, and this is just a technicality. By the rules of significant digits, this should actually be 15.35, and here's the reason why. She had 3 significant digits here, and she went out to the tenths and the hundredths place. 8.00 is also to the hundredths place, and when you add or subtract, you line up the decimal places. So I wouldn't take off a point from this, but this is just like a procedural thing. This should actually be 15.35 meters because she was adding those numbers together. And they were both out to the hundredths place. So I wouldn't take off a point, but this is just kind of how science is done. So that should actually be like 15.35 meters. So that's one way to do this, and it's beautiful. If it were me, this is how I would have done it, okay? Because this is going off of known values, right? There's 2 other ways that you can work this problem. This is what I would have done, simply because of the fact that, yes?
This,
Yeah, here, okay. Just give me, I'll hand them out. There we go. Thank you. Okay. Go with the mailman. Okay, now, here's the second way that you can do this problem. You're going to use that distance equals 1.5 feet plus v naught times time. Remember, what you're going to have on the test tomorrow is a laminated version of your equation sheets. The yellow one and the purple one. This is not on that equation sheet. Okay, it's not there. But all this is just like an average velocity. You add the 2 velocities together, you divide by 2, multiply it by time. That's basically what we're saying. In terms of an average velocity, okay? So, now, here's what's going to be important. Who did this one? Huh? Okay, now, see what you did here? Technically, you're subtracting this. What should you actually be doing? That should actually be adding, okay? So, it's not a big deal, but I'm just saying, technically, you should be adding that. Now, what's the disadvantage of this? What did you have to use? You had to use that time up. So if this time up is wrong, that maximum height then becomes wrong, okay? Now, in this case, you were fine. But that's the roll of the dice that you have, okay? Now, here's the third way you can do this. If you are a geometry kind of person, you could go to your velocity time graph, okay, and this is I think what Gannon was rolling, and say, oh look, here's a triangle. Here's a height of 12 meters per second. Here's the base of 1.22 seconds, because that's how long it took to go to 0. Find this area, which looks surprisingly like 1/2 base times height, which is what we basically did up above, okay? So, if you want to use your velocity time graph and find this, hey, that's cool. It's fantastic. But again, here's the problem. If this time is wrong, guess what? Your maximum height is going to be wrong. Okay? So it's a roll of the dice. Doesn't make any difference to me how you do it. Just know how to do it. All right. So we're good with that. Now, time down. There's a couple of different ways you can calculate the time down. If it were me, this is what I would have done, what Ryan did. Okay? This is what I would have done. You have to realize on the way down, you're going to start at 0. So if you want to think about that on the way down, it's just like it's a completely separate problem. You're dropping a ball from 15.35 meters high, and it's going to fall. How it got there doesn't make any difference. Whether I throw it up in the air and have it fall, or if I just hold it up there and drop it, doesn't make any difference. Either way, the initial velocity is going to be 0, and it's going to start from rest. So, but this is what's really nice about what Ryan did. Notice in here, he had a negative displacement, because it's falling from 15.35 to 0. So I'm going to look for this on the test. You've got a negative value here. I'm going to have a negative sign underneath this radical. Okay? So we're going to have 2 negative values here, right? So with those 2 negative values here, that's going to give me my time. So on the test, don't do this. Don't make this positive and that make negative. Or worse yet, make both of these positives. Because then it's just like you've completely changed the parameters of the problem. So this is one way that you can do this, and it's cool. Okay? This is what I would do. But there's another way which we'll get to in just a second. Now, on the final velocity, and again, there's more than one way to do this. Joel, you did this one too, didn't you? So, here's what's important if you're going to go with this one. You know on the way down, your initial velocity is 0. Okay? It's cool. You're starting from 0. If you're going to do that, then you're going to use the entire distance down to 15.35. So this is another way that you can approach this problem. Technically, when that ball crosses back down, it's going to be going like negative 12 meters per second. So you could actually put in negative 12 meters per second here as an initial velocity. But then, over here on that distance, you're only going to use 8 meters. Because it's going to start at 12 and it's going to fall for 8 meters that way. I don't care what you do. If you're going to start at 0, use the entire height. If you're going to use negative 12, because that's how fast it's going when it gets back to that point, then you're going to use 8 meters here. But you can't cross over. You can't start at 0 here and then put 8 meters here. And you can't start at negative 12 here and use the 15.35 over here. I don't care what you do, but you got to be consistent. And here's the other thing that's nice about what Joel did. Notice that I've got this negative sign underneath the radical here. I got a negative sign here for that negative 9.8. That's going to get me positive numbers underneath that radical. And there you go. Now, this is where your calculator will lie to you. Your calculator is just going to tell you the answer is 17.3 meters per second. Okay? So what you have to do is choose the negative root and realize that like the square root of 4 is plus or minus 2. That's what you've got to do here. Okay? You just have to choose that negative root. So This is nice. It works. It's fantastic. Now, is there another way that we could find the final velocity using time? That time down. What can we do there? What equation could we use?
The time equals final velocity minus initial velocity over acceleration.
Yeah. So the other thing that you could do is what it's going to start off is v equals v naught plus at. So on the way down, so you're here, right? On the way down, what's your initial velocity? 0. So you got an acceleration of negative 9.8 meters per second squared. Now here's what you have to watch, okay? If you're going to start at 0, then you only use the time down, okay? From 0, so you're going to use this time of from 1.22 onward, and you're going to use that, what did we get? What did you get, Ryan? 1.77? Okay? So you're going to put in 1.77 seconds. It's like a slope-intercept. The line is starting at 0 meters per second. You're coming down like this. So you're going to use 1.77 seconds. Now, if you wanted to, you could make 12 meters per second as your initial velocity, because that's actually where you're starting. But if you're going to do that, then you've got to use the entire time of 2.99 seconds. Okay? So you could use v naught as 12 meters per second plus negative 9.8 meters per second squared times 2.99 seconds. You're going to get the same answer either way. The advantage of this one is that it's automatically going to generate a negative value for your velocity. You don't have to choose the negative root, okay? And you don't have as much to muck with squares and square roots and all that good stuff. So this one mathematically is probably a little bit simpler because it's just negative 9.8 meters per second squared times multiplied by the time down, okay? Doesn't make any difference to me. But that's why I said this is where there's a little bit of creativity on how you work this problem. So here's what's going to happen on the test. This is going to be the last problem on the test. Okay? On the review, so let me explain how I do reviews initially here at the beginning with you guys. I'm going to give you a set of blank questions, types of problems you got to be able to do on the test. I'm going to give you the answer key with them all worked out. Okay? This is going to be one of the problems that's going to be on the review. Do not hand the review in to me. It is not an assignment. This is why I'm giving you the answer key so that you can make sure you know how to work the problem, so that you know if you're doing them right. Okay? Go with that. What I would do is that I would not even breathe on that answer key. Okay? I would file it away and not even look at it. I would work that entire review, then look at what I did. Because here's the problem. If you're looking at what I did, it's like, oh yeah, God, I would have worked it, Burkamp, God, you were spot on. I would have worked it the exact same way, okay? You know, it's like, no, okay? I know how to work the problem. I'd hope you'd agree with how I did it and got, you know. So what I would do, I would start over from scratch. You all have everything back to you, okay? Especially those big acceleration assignments, okay? If you've missed anything, I'd go back and I'd figure out what you did wrong, all right? Just a word of advice. Okay, so we got 15 minutes left, so here's what you're going to get. This sheet of paper is going to tell you the big topics that you're going to know for the test. There are certain golden rules. Go back, and you know I'm going to ask you about velocity time graphs, position time graphs, acceleration time graphs. Remember, if something's speeding up, what do you know about velocity and acceleration? They have the same sign. There's no exceptions to that rule. If something's slowing down, they have to have opposite signs. So let's say, for example, you have an object rolling down a hill, okay? And if it's rolling down the hill, let's define down as being negative, okay? So if it's rolling down the hill, just you let go of it, and you're just letting it roll down the hill. What's going to be the sign of your acceleration vectors? Positive or negative? Why?
Because they have to be the same for speed up.
Yeah. So you would have like negative V1, and you'd have a bigger negative V2, and you're going to have some negative acceleration. Now, but let's say then you hit the brakes, and you bring the car, and you stop your car as it's rolling. Then what's going to happen to your velocity vectors? What are they going to start to do? They're going to get smaller, so you're going to go from some big negative 2 to some smaller negative V1. So then which direction is your acceleration vector going to point? Up the hill, right? Now, that's one way that you can view this problem. You should also be able to visualize this thing in terms of a velocity time graph. So you're going to start off and you're going to have some negative velocity that's getting bigger. So how are you going to show that on a velocity time graph?
Straight.
Start here and it's going to go down like this, right? Negative velocity, negative acceleration, you are. Then you hit the brakes, what's this going to do? It's going to go up towards 0, right? Now, if I stop it and make it go back up the hill, then what's that graph going to do? Yeah, then it would keep going up like this. Is it possible to change direction with constant velocity? No, because what 3 things do you have to do to change direction? Slow down,
Speed up.
speed back. Now, is it possible to change direction with uniform acceleration?
Yes.
Yeah, look at the graph, okay? You have uniform acceleration because you have the same slope the entire time. So here I've got negative velocity and positive acceleration. What am I doing? Slowing down. Now I have positive acceleration with positive velocity, and I am speeding up, okay? True or false? Negative acceleration always means that you slow down.
False.
False. How can you speed up with negative acceleration? Yeah. That's what's happening right here. Okay? Get out of your minds that negative velocity means that you're going backwards. Okay? It doesn't. Negative velocity just means you're going in a particular direction. Okay? That's all that means. Anyway, so there's that. So here's what's going to happen on Wednesday. Okay? On Wednesday, I'll just give this to you all. I just don't want to waste time tomorrow with text. On Wednesday, I want to dump out another YouTube video that's on the graphical addition of vectors. Okay? You're going to have an assignment. That's what's going to happen on Wednesday, and then we'll finish it on Thursday. Okay? And so you guys will have to zoom in or watch that video. No, you guys will actually be here on Thursday. It's the other group that will have to watch that. So, okay, I'm done. I'm going to hand out the stuff. Okay? You've got your assignments back, so you should be in good shape there. And you have the rest of the time. I would suggest just work on that review. So I'm done. So stop that. Zoom.